You know, when we look up at the night sky, we see this incredible variety.
Hmm.
We see stars, we see galaxies clustering together in these massive glowing webs. We see planets, and we see us.
Right.
We exist. But there is a massive paradox hiding right at the beginning of that story.
Oh, yeah, there definitely is.
Because when we look at the very earliest light in the universe, the cosmic microwave background, it is almost perfectly uniform.
Exactly.
The temperature is basically the exact same in every direction.
Mm.
But a perfectly uniform cosmos could never build stars or galaxies or planets. I mean, if everything is perfectly smooth, gravity has absolutely nothing to grab onto to start building the lumpy universe we live in today.
It's arguably the ultimate cosmic paradox.
Well,
You need perfect smoothness to match what our telescopes see in that ancient background radiation.
right.
But you absolutely require tiny irregularities to actually form the structure of the universe as we know it.
Yeah, so to solve this, cosmologists had to invent one of the most mind-bending theories in scientific history, which is inflation.
It really is wild.
Today, we're doing a deep dive using Alan Guth's landmark book, The Inflationary Universe, The Quest for a New Theory of Cosmic Origins. We want to figure out how a fleeting, almost unimaginably brief period of accelerated expansion could iron the universe flat while simultaneously planting the seeds for every galaxy in existence.
Yeah, Guth's book is a brilliant piece of scientific history. It really shows how a frustrating problem in particle physics ended up completely revolutionizing our entire framework of cosmology.
We have a lot of ground to cover today, but the path is incredibly fascinating. Okay, let's unpack this. We're going to tear apart the standard hot Big Bang framework, figure out why cosmologists were losing sleep over three major headaches,
The big three.
right? The horizon flatness and magnetic monopole problems. And then we'll look at Guth's wild solution, which is a false vacuum driving exponential expansion.
Which is a whole concept on its own.
Oh, absolutely. We'll trace how his original model actually failed to work, how the physics community rallied to save it with new and slow role models, and how a mysterious reheating phase gave us the hot universe we know. Finally, we'll look at how random quantum fluctuations seeded the galaxies. We'll review the actual satellite data from Kirby WMP Planck and the BICEP Keck missions.
Yep, the observed evidence.
And we'll try to separate the hard science from unresolved questions about the inflating primordial gravitational waves, eternal inflation, and universe creation.
That's a lot.
Now,
But to understand the sheer brilliance of the solution, we really need to set the stage with what the scientific community thought they knew before inflation came along.
yeah, let's build that cosmic timeline, starting with the hot Big Bang framework. First off, we really need to correct the mental image almost everyone has.
Of the explosion myth.
Exactly. When people hear Big Bang, they picture a grenade going off.
Right.
They picture debris exploding outward from one central point into some pre-existing dark, empty room of space. But cosmic expansion is not debris exploding through space.
It's definitely not. The Big Bang wasn't an explosion in space, it was an explosion of space.
Okay, wait, explain that.
So cosmic expansion means that the fabric of space itself is stretching. It's increasing the distances between co-moving locations.
Co-moving meaning what?
Meaning points that are just sitting still in space are getting further apart because the grid itself, the space between them is expanding.
Oh, I see.
People sometimes use the raisin bread analogy where the dough expands and the raisins move apart. But the key takeaway is that there is no center to the expansion.
Right.
Every point in the universe sees everything else moving away from it.
Okay, but before we start throwing inflationary physics at this, we have to be really careful here to separate what we've actually seen through telescopes from the math we use to explain it. Not all of this science is on the exact same footing.
Right, and that is a fundamental rule in cosmology. We have distinct categories of knowledge.
Okay.
So the expansion of the universe itself, the maps of the cosmic microwave background, the abundances of light elements like hydrogen and helium that were forged early on,
Yeah.
those are proudly observed. We have measured them with instruments.
They're hard data.
Exactly.
Okay.
Meanwhile, the underlying framework we use to understand gravity and space, Einstein's general relativity, is theoretical.
Right.
It's a spectacularly successful theory, but it is a framework of rules, not a direct physical object we can hold.
Right. So we have this observed expansion and this theoretical framework of relativity. But when cosmologists ran the clock backward using just the standard model, they hit three massive walls.
Yeah, they really did.
Let's paint a picture of these puzzles, starting with the horizon problem. So imagine you have 2 cups of coffee on opposite sides of the known universe.
Okay.
You measure them, and they are the exact same temperature down to a fraction of a degree. But they are so far apart that light hasn't had time to travel between them since the beginning of time.
Right, they're totally disconnected.
They've never been in causal contact. So how did they know to be the exact same temperature without ever sharing heat?
What's fascinating here is that while the coffee analogy works for visualizing the temperature equilibrium, we need to look at the actual physics. The horizon problem is specifically about widely separated regions of the cosmic microwave background, the CMB.
Right, the early light.
Yeah, when we point our telescopes at opposite sides of the sky, those regions have nearly identical temperatures.
Right.
But in a simple non-inflationary timeline, their past light cones never intersect. There was never a moment in the history of the universe where they could have interacted to equalize their temperatures.
They simply shouldn't know about each other.
Exactly.
They shouldn't.
Which is deeply unsettling for physicists.
It's very.
Then we have puzzle number 2, the flatness problem. I like to imagine trying to balance a perfectly sharpened pencil exactly on its tip.
That's tough.
Right? If it leans, even a fraction of a millimeter, gravity pulls it and it falls over faster and faster. In the standard model, the geometry of the universe is just like that pencil.
Mm-hmm.
Normal decelerating expansion should magnify any tiny initial curvature over billions of years. If the universe started out even slightly curved by today, it would be massively curved.
Right. It would have either collapsed back in on itself or blown apart so fast that galaxies could never form. Yet the universe we observe is incredibly close to being spatially flat.
Standard expansion drives the universe away from flatness, making its current state wildly improbable without some balancing mechanism.
Right.
However, we have to be careful with the conclusions we draw here. The pencil analogy is good for understanding the instability, but accelerated expansion does suppress observable curvature, making our local patch look flat.
Oh, okay.
But a near-flat geometry in our observable horizon does not prove that space is infinite, nor does it prove that the total global universe is completely flat.
It just means our specific observable bubble was stretched incredibly taut.
Exactly.
Kind of like standing on a frozen lake, it looks perfectly flat to you locally, even though it's wrapped around a spherical planet.
That's a great way to think about it.
Finally, puzzle number 3, the monopole problem. In the 1970s, particle physics theories predicted that the extreme heat of the early universe should have spawned these massive, stable particles called magnetic monopoles.
Right.
Basically heavy magnets with only a north pole or only a south pole. They should be cluttering up the cosmos.
They should be everywhere.
But we look out and we don't see any.
Fun fact, Alan Guth wasn't actually trying to solve the horizon or flatness problems initially.
Yeah.
He was a particle physicist obsessing over where all the magnetic monopoles went.
Oh, really? I didn't know that.
Yeah, the grand unified theories insisted they should be there, but the universe was seemingly swept clean.
Which brings us to Guth's revolutionary proposal to clean house, which is a brief, intense period of accelerated expansion. He argued this was driven by a scalar field in a high-energy state called a false vacuum.
Right.
Think of a stretched rubber band. It's holding a ton of stored potential energy. In physics, this high-energy vacuum state actually possesses negative pressure.
Mm-hmm.
And in general relativity, negative pressure creates a repulsive gravitational effect driving exponential growth.
It pushes out.
Right? This massive stretching dilutes the unwanted relics like monopoles, and it takes a tiny, formally connected microscopic region and stretches it so huge that it solves the horizon problem.
Yep.
Our 2 sides of the universe actually were in contact before inflation ripped them apart.
The mechanism solves the puzzles beautifully.
Wait, hold on. I need to pause on the negative pressure thing.
Sure.
On Earth, pressure pushes things outward like air in a balloon. How does negative pressure push space apart? Shouldn't negative pressure suck things inward?
It's highly counterintuitive. I mean, in classical physics, yes, negative pressure is like a vacuum pulling inward.
Right.
But in general, relativity pressure actually contributes to the gravitational field. Positive pressure adds to the gravitational pull. So negative pressure creates a negative gravitational pull, meaning gravity becomes repulsive.
Oh, wow.
Yeah, it pushes space itself apart.
Okay, that kind of makes sense. Relativity is just weird.
It really is.
Yeah.
But I also want to clarify how people visualize the false vacuum itself. A false vacuum is not ordinary empty space. The specific scalar field and the shape of the potential energy curve that Guth proposed is not an observed object.
It's not physical like a particle.
Right. It is a model-dependent choice.
Hmm.
We are assigning specific mathematical properties to a hypothetical field to make the equations align with what we observe later.
Yeah.
We haven't caught a false vacuum in a jar.
Yeah, and actually, if you run the numbers on Guth's original idea, what we now call old inflation, it had a fatal flaw.
It did.
He proposed that this inflation ended when bubbles of true vacuum started forming inside the rapidly expanding false vacuum, kind of like boiling water.
Right.
The energy of the false vacuum would be released as these bubbles collided. But the math showed a massive problem. Space was expanding so exponentially fast that the bubbles were being driven apart faster than they could grow.
The bubbles simply couldn't catch up to each other to merge.
It's like trying to merge on the highway, but every other car is accelerating at light speed.
Yeah.
You're never going to form a smooth flow of traffic. They couldn't create the perfectly smooth universe we see today. It was a completely chaotic end to inflation. They called it the graceful exit failure.
And, Guth was incredibly honest about this failure in his work. He treated the math with real integrity.
Which is great.
And this is a testament to the scientific process. The physics community looked at this graceful exit failure and recognized the immense power of the inflationary framework anyway.
Right, because it solves so much else.
Exactly. It solved the horizon flatness and monopole problems so elegantly that physicists knew the broad paradigm was likely correct, even if the specific microscopic mechanism of those bubbles was definitively flawed.
That structural failure led directly to a major breakthrough. Enter new inflation and the shift to slow roll models. Yeah, here's where it gets really interesting. Instead of this violent bubbling process, physicists shifted the mental picture.
Okay.
Imagine a ball rolling very, very slowly along a high, flat plateau on a hill. That plateau represents the potential energy curve of the field. As long as the ball is rolling slowly across the flat top, the universe experiences sustained exponential expansion. But eventually the plateau curves downward. The ball rolls into the valley, and inflation ends smoothly everywhere at once, without the chaotic highway merging bubbles.
The slow roll dynamics saved the theory entirely. It allowed for enough exponential expansion, enough e-folds, to use the technical term, to flatten and smooth the universe, while providing a mechanism to end inflation uniformly.
But wait, if inflation expands space that violently and stretches everything out to astronomical sizes, it also cools everything down to incredibly close to absolute zero.
Right.
The universe becomes a freezing empty void. So where does the hot Big Bang come from? How do we get the blistering heat and the particles that eventually made us?
That requires a mechanism called reheating.
Reheating, okay.
Yeah, as your ball rolls off the plateau and down into the valley, as the scalar field drops to its minimum energy state, it doesn't just stop, it oscillates.
Like sloshing around.
Exactly. It sloshes back and forth to the bottom of the potential well. This rapid oscillation creates immense friction, and the energy stored in the inflationary field decays.
Oh, wow.
It dumps that energy, converting it into a hot plasma of ordinary particles and radiation. The universe is suddenly flooded with heat and light.
So inflation happens first, empties everything out, and then reheating triggers the actual hot Big Bang phase.
Exactly. But again, let's keep our scientific buckets clear here.
Right.
The slow roll dynamics, the behavior of these quantum fields, and the overarching concept of reheating are theoretical. We understand how they could work in principle.
But we haven't seen them.
Right, the exact temperature the universe reached, the specific reheating histories, and the exact shape of that on potential hill. Those remain highly model dependent. We have dozens of theoretical models that work on paper, but we don't have the final answer on which one the universe actually used.
All right, so inflation smooths everything out, it flattens the geometry, it dilutes the heavy monopoles, and it ends by dumping energy to create a hot bath of particles. But we are back to our central paradox. We needed a mechanism to explain the smoothness which inflation provides.
Right.
But we also needed tiny irregularities for gravity to grab onto to build galaxies. If inflation is a cosmic iron that irons out all the wrinkles, where do the seeds of galaxies come from?
This is arguably the most profound part of the entire framework. The answer lies in quantum mechanics.
Okay.
Even in a perfectly empty vacuum, the Heisenberg uncertainty principle dictates that energy isn't completely stable. Yeah. There are constant microscopic quantum fluctuations, random subatomic jitters, where energy briefly spikes and dips.
Right, standard quantum weirdness.
Exactly. Normally these vanish instantly. But during inflation, space is expanding so incredibly fast that these microscopic jitters are caught frozen and stretched to macroscopic cosmic scales before they can disappear.
That is just wild to think about.
It really is.
Inflation takes random subatomic static and blows it up to the size of solar systems and galaxies. Those stretched out quantum jitters become the primordial density variations. A tiny microscopic region that randomly had slightly more energy gets magnified, and eventually that slightly denser region has slightly more gravity. Over billions of years, it pulls in dark matter and gas to become a massive cluster of galaxies.
It's amazing.
We are literally walking around inside a magnified quantum fluctuation.
And this is where the theoretical elegance meets the cold, hard data. Guth published his book back in 1997, but the modern astronomical community had spent the last 2 decades looking for the fingerprints of these stretched fluctuations.
Right.
Successive space missions like COBE, WMAP, and the Planck satellite have mapped the cosmic microwave background in incredible detail. They measured tiny temperature fluctuations in the sky patches that are 100,000th of a degree hotter or colder than the average.
I mean, these variations match what inflation predicted.
They do. If we connect this to the bigger picture, the satellite maps of the CMB, along with the clustering of galaxies, the constraints on spatial curvature, and the polarization measurements of the background light are observed realities.
Oh.
The data shows a primordial spectrum of fluctuations that is very close to scale invariant.
Meaning the clumping looks statistically similar whether you zoom in on a small patch of the sky or zoom out to a massive scale.
Precisely. The data also shows the fluctuations are Gaussian, meaning the distribution of those hot and cold spots follows a standard bell curve, which is exactly what you'd expect from random quantum noise. And they are adiabatic.
Wait, adiabatic. Does that mean the fluctuations in the dark matter and the regular radiation are perfectly in sync with each other?
Yes. If a region has 1% more dark matter, it also has 1% more photons. All these statistical properties perfectly support broad inflationary expectations.
Wow.
It is a massive victory for the paradigm. However, it is vital to note that these observations do not directly identify the specific inflatant particle, nor do they uniquely prove one single potential hill.
Right.
They support the overarching framework, not a specific microscopic model.
With a topic this sprawling and bizarre, it is so easy for popular science to take a metaphor too far or jump to wild conclusions.
Oh yeah, all the time.
Let's tackle some of the things people constantly get wrong about this, starting with the expansion itself. I always hear people conflating inflation with dark energy.
Right.
But inflation is not the ordinary expansion of the universe we observe today, right?
No, they're entirely different eras. Dark energy is causing accelerated expansion right now, but at a vastly slower rate and at a much lower energy scale than primordial inflation.
Okay.
They might be mathematically related somehow, but they are not the same event. Furthermore, inflation does not automatically explain the absolute beginning of time.
Right, it tells us what happened a tiny fraction of a second after something started, but it doesn't give us the moment of creation itself.
Exactly.
What about the physical field itself? We keep talking about the inflaton.
The exact inflatant particle or field has not been discovered. We simply haven't built a particle collider capable of reaching the energy scales required to find it, assuming it even interacts with standard particles in a way we can measure.
No, I thought we had already proved inflation definitively by finding gravitational waves. Didn't a telescope at the South Pole detect that a few years ago? I remember seeing headlines about B-mode polarization.
Ah, you're thinking of the BICEB2 announcement from 2014, which turned out to be interference from galactic dust.
Oh, right, the dust.
Yeah, B-mode polarization would be the signature of primordial gravitational waves, essentially stretch marks on the fabric of space-time caused by the violence of inflation.
Sure.
Detecting those B-modes would be the smoking gun for the specific energy scale of inflation. But as of the 2024 BICEP constraints, it's not yet a detected primordial signal. We have very tight limits on it, but no confirmed detection of tensor waves from inflation.
Okay, here's another one I always assumed. Doesn't inflation solve the antimatter problem too? If it created all the particles during reheating, doesn't it explain why there's more matter than antimatter?
It actually does. Yeah, inflation alone does not explain the matter-antimatter imbalance. Inflation just creates the raw energy and the heat. The process of converting that energy into an unequal amount of matter versus antimatter is called baryogenesis, and it requires additional complex particle physics beyond standard inflation.
So inflation sets the stage, but it doesn't write the script for the particles.
That's a good way to put it.
What about Guth's concept of the ultimate free lunch? He argues that the positive energy of all the matter in the universe is exactly balanced by the negative energy of gravity, meaning the universe could arise from zero total energy. That sounds like a mathematical proof that the universe came from nothing.
It is a compelling philosophical idea and a very useful heuristic intuition.
But
But the accounting of global gravitational energy in general relativity is incredibly subtle and complex. You can't just tally it up like a spreadsheet. So while the ultimate free lunch is a great way to think about how you can get a massive universe without violating energy conservation, it is not a mathematically demonstrated accounting identity for every possible cosmology.
I'm glad we cleared those up. Now I want to push into the truly wild stuff, because the last few chapters of Guth's book get into some seriously speculative frontiers.
They really do.
He talks about eternal inflation. The idea is that if quantum fluctuations are random, there will always be some regions where the false vacuum randomly jumps up the energy hill instead of rolling down.
Right.
In those regions, inflation never decays. It just continues forever, constantly spawning new pocket universes, creating an infinite multiverse. He even touches on universe creation ex nihilo, or making universes in a laboratory.
We have to step carefully here. Concepts like eternal inflation, multiverses, wormholes, and creation from nothing proposals are highly speculative.
Okay.
They are fascinating logical extensions of the mathematics, and many physicists take them seriously. But they are entangled with deeply unresolved issues, most notably the measure problem.
The measure problem, what's that?
How do you even calculate the probability of something happening when you have an infinite number of pocket universes being created constantly?
Rabia.
Standard statistics break down. We don't know how to handle it. These multiverse ideas have far weaker evidentiary support than the CMB maps or the observed expansion of space.
That makes sense.
Additionally, things like the exact count of E-folds, the amplitude of those undetected tensor waves, and the initial conditions of the universe before inflation began remain strictly model-dependent. We cannot treat the existence of a multiverse with the same certainty as we treat the existence of helium.
It sounds like we have a brilliant blueprint, but we're still looking for the exact materials the house was built with. So what does this all mean? Synthesizing all of this, the inflationary universe remains an incredibly engaging first-hand history of a framework that completely transformed cosmology.
It really did.
It elegantly links the deepest conceptual puzzles of the Big Bang to the microscopic quantum structure that eventually formed us.
It is an undeniable triumph of theoretical physics. However, the final scientific assessment is this. While inflation is overwhelmingly the leading early universe paradigm, it is not a verified microscopic mechanism.
Right.
Its fundamental field identity, the exact energy scale at which it occurred, and the final specific model remain deeply mysterious. We know a period of rapid expansion happened, but we don't know exactly what physical engine drove it.
The frontier is always moving, and that's what makes it fun. Just a quick note for our audience, this deep dive has been an independent Cosmora HQ book overview. It is not an official or complete audiobook. We highly encourage you to access Alan Guth's published book for his complete history, the brilliant diagrams, and his full arguments.
Absolutely, check it out.
Please subscribe, leave a comment, and share this with your fellow space nerds.
And to leave you with something to ponder, consider this. If inflation explains several cosmic puzzles, but its field and energy scale remain unknown, what observation would turn a powerful paradigm into a specific physical theory?